Okay, this is these two problems right here, where we look at light entering into a piece of glass that has this particular shape with a refractive index of 1.5, and you're asked to finish the ray diagram to show the reflected and the refracted rays and indicate all exact angles. You're asked to do the same thing down here. So let's go ahead and attempt to do that. I am going to pull up a clean sheet of paper. So here, this is going to be a little tricky to draw. Remember, this is a 45-degree angle, so I'm going to go down 2, 4, 6, 8. I'm going to go down 8. I'm going to draw this as best I can as a 45-degree angle, and knowing that this should also be a 45-degree angle from this. Okay, so the situation that you're given is kind of a special case situation in that you have a ray coming in straight on, perpendicular to the surface. The special case is that even though this is the refractive index of 1, and this is n equals 1.55, even though this has a different refractive index, the transmitted ray, because it's perpendicular, the incident ray will also be straight ahead, and it will hit this here at another, creating another 90, 45, 45 triangle. So this angle is now 45 degrees. And note that the reflected angle here, let's just be concerned with the reflected angle. This one will also be 45 degrees down here, making another 90, 45, 45 triangle, then creating another reflected angle at 45 degrees here, and then becoming incident on the initial interface and transmitting through there. So the angles that we see here are all 45, 45, 45, 45, and 45. So the light takes this path here inside the prism. Now, what happens when it encounters this, and does in terms of going out, does it go out, or is it a total internal reflection? So we would need to put down a perpendicular to this surface and a perpendicular here. So these, you can see that what happens is sort of equivalent here, and the refractive index is here 1 and equals 1 over here. So what about the transmitted wave? Well, I'll use a different color for that. Transmitted wave, let's use Pete's an analog of the car with the wheels. So the first wheel to hit, if there are wheels here, is this left front wheel. The refractive index lower, so it's slipperier. So we expect the wave to actually turn in that direction since it's more slippery. So we expect to get a light ray coming in at this angle here, and that we expect the angle to actually increase. So we expect the angle to be like this. And maybe this is an exaggeration, but you can see this incident angle is right here. This is the incident angle, and here is the next angle, the exiting angle. So it does the same thing here. We expect, here's the incident angle, 45 degrees. We're expecting it to be more than 45 degrees. And then in this case, it goes straight through. Okay, what are the angles? Well, we can use Snell's law here. N1 sine theta 1 equals N2 sine theta 2. N1 is 1.55. I think I have that right. 1.5, excuse me, 1.5 sine of theta 1, sine of 45 degrees equals 1 times sine of theta 2. So we're trying to figure out what this angle theta 2 will be. Okay, so this we have 1.5 times the sine of 45. And the sine of 45, this is 45 triangle 1 root 2. Sine of 45 therefore is 1 over root 2, 1 over square root of 2 equals sine of theta 2. Now I see I have a bit of a problem here because I have 1.5 or 1.4 something. So the sine is greater than 1. So that makes me suspicious. It makes me think maybe we've exceeded we've met the critical angle. Let's see if we can calculate the critical angle for this particular situation, because of course the sine can't be bigger than 1. So 1.5 sine of 45. Oops. 1.5 sine of the theta crit equals 1 times sine of 90. We know sine of 90 is 1. So we have sine of theta crit is 1 over 1.5. So the thing I want to point out is that we know the sine of 45 is equal to 1 over 1.4 something. So we know the sine of 4590 is 1 over 1.4. If this is actually bigger, this is longer, then we know that the angle is actually smaller. Okay, I'm exaggerating here. 1 over 1.5. That means this angle here, theta crit, is less than 45. So in this case, we actually do not get these it's total internal reflection is what I'm saying. We've exceeded the critical angle. So what we need to do to adjust this image then is actually get rid of these guys to show that we have total internal reflection. And you know what that would do is, boy, there'd be rays that would kind of come in here and maybe bounce all over the place. I'm not going to actually attempt to draw those, but I'm just going to leave it like this and say this is total internal reflection. The rays are refracted as shown here, but there's no other rays that come out of the prism.